In the last video, I've talked about how to find the average power in a resistor such as a light bulb that is connected to an alternating current. And the answer was that it is just half of the maximum power in the light bulb. Now let's go back to look at this equation that relates power to the voltage. For example, we know that power is equal to V squared over R. So if we can find an average value for the power, which is quite convenient. It's always convenient to have an average value because the actual value goes up and down. It's a lot more complicated. So then wouldn't it be useful also if we can have an average value for the voltage, since the voltage is also changing all the time? And it will be useful, except that it's a little more complicated in this case, because since the voltage keeps changing direction, it can have positive and negative values equally often. And that means that if I just take a simple average of this, I'll get 0, right? Because the voltage is sometimes positive and sometimes negative. So if I add this up, I'll just get 0 on average. And that is obviously not useful, right? If I say that average voltage is 0, then I have no idea that it's actually 0 all the time, or it's actually changing, or how much it's actually changing, and or how big the peak value is. So there has to be another way to do this. Now if you look at this formula, one way to think about it is to look at this formula and think about what is the value of V that can give me the average power. Okay, I know that V itself keeps changing, and therefore P changes with time. But since I can get an average P, since I know that the average power is half of the maximum of the peak power, okay, so can I then find the corresponding V that will give this average power? Right, we can. That should be quite easy. So let's try that. So what I want to do is this. Okay, let me write down what I want to do. In this formula, P equals to V squared over R. Okay, what I want to do is this. I want to find the value of V that gives P equal to half, that gives P equal to the average power. Okay, that's what I want to find. Right, so let this V be, say, V1. Okay, let the answer be V1. Now the average power, we already know the average power, that the average power is half of the maximum power. Okay, so I can substitute this into there and then solve for V1. So let's do that. So this is V1 squared over R. Okay. Now if I rearrange this, I would get V1. I would get an expression for V1. But instead of just doing that, let me do it this way. It would be useful to have the answer in terms of the peak voltage, because after all, it's it is a voltage. The quantity that we want to find is a voltage. So it would be useful to express it in terms of the original peak voltage. And we know how P0, the peak power and the peak voltage is related. Okay, they are also related by this formula. The peak power P0 happens when the voltage, the actual voltage itself, is at the peak. Okay, so we know that P0 itself is equal to the power you get when the voltage is at its peak. So just using the same formula, we can write this down. Okay, and using this, I can substitute this into the P0 here. So P0 is V0 squared over R. And this gives V1 squared over R. And now you see you can cancel the R. You can cancel the R, and then I have V1 squared equals to V0 squared over 2. Finally, if I take the square root, I get V1 is equal to V0 over square root of 2. And this gives us the voltage, which gives us which would give the average power in this formula. Okay, you can think of it as if you imagine that I replace the alternating currents by, say, a battery that gives a direct current, then this is the voltage of a battery that I would need to give the same power or same brightness in the light bulb, in that sense. So this expression here is also a kind of average, but it's not the average in the normal sense. How can we understand this? How can we understand why a bit more about this? There is a way to understand this, and in fact, we need to actually understand this. Now, the name of this expression is called, or of this type of average is called, the root mean square. We shall try and understand what this means physically and how this name comes about. So what I'll do is I will think about actually deriving. Alright, to do this, I'll think about deriving the average power in another way, starting from the voltage. Now we know what the voltage graph looks like. It's a sine function, so it looks like this. It goes up, down, down. That's the period T, and that's the peak voltage V0. And we also know how voltage and P are related. And in the last video, I've explained how to find the average power. Now what I want to do now is, instead of looking at the power directly, let me look at V squared. Let me look at trying to find the average V squared instead. of the average power. Because if I can find the average V squared, then I can just divide it by R to get the average power. So it's another way to do it. So let me try this. I'll start with taking the square of the V. If I take the square of V, it's the period. That's by 0, that's by 0, that's by 0 again. If I take the square of V, so this is V squared, then that all the negative part of the graph would become positive. So the graph would look like this. So this is essentially a sine-squared graph as well. Okay, this is V0 squared. So this is actually V0 squared sine squared omega t. No, squared sine squared omega t. And we know how to deal with a sine squared graph from the last video. We know how to find the average if the graph follows a sine squared pattern. And it's the same if it is multiplied by a fixed number, right? It doesn't change the nature of this graph, meaning that if I draw the halfway line, through this graph, the top part of the graph is symmetrical to the bottom part. So I can just take this area and fill in this area below the halfway line. And they will fill exactly because they are symmetrical. So I just cut out this area and fill out this part. And the effect of this is that, and I just do it to the whole graph, right, all the way until maybe infinity. Just do it for everything. So if I do that, that would give me the average. Right, using the same reasoning as in the last video, we can conclude that the average of this V squared, the average of V squared is just half of V0 squared. So let me write out this results. So I would say that the mean. Now I'm going to use the word mean now instead of the word average. So for a reason that will become clear afterwards. So I'm just going to say the mean of V squared is equal to half of V0 squared. Right, because V0 squared is the peak value. Remember, we did something very similar for the power in the last video. Where I took half of the peak power. So now that we have found the mean of V squared, that gives us a kind of average value of the V squared. I can take the square root of this. Right? If I take the square root of this, I will get the roots. Let me take the root of the mean of this V squared, which is the square of V. Okay, the square of V is just V squared. Now I'm intentionally writing this out in full because I want to explain in a moment the origin of this root mean square term. So okay. So the mean of the square of V is just the mean of V squared, right? Which is this. Now if I want to take the root of the mean of the square of V, that means that I want to take the roots of this, right? I want to take the roots of that. And then I get V0 over root 2. Now if you remember from what I did maybe 5 or 10 minutes ago, this is exactly the voltage that will give me the average power. if I put it into this formula. Okay. And in this way, right, in this way, we can think of this method as another way to derive the average power. Okay, or we can think of this as an alternate way, right? That means another way of finding an average value for V. Right? We know that we can't just find a simple average by adding up the V's over time, because it is positive and negative equally often. So if I just add up the voltages in a simple way, I'll just get 0 if I try to take the average. But using this way, by squaring it first, I remove all the negative values, okay, and then taking the average, okay, and then taking the roots again, so that I get back, instead of V squared, I get back a voltage value, a voltage quantity. It's kind of an alternate way of finding average. Okay, so I can think of this as one kind of average as well, not the simple kind, which we can call the mean. Right, that's where the word mean comes in. Mean is a kind of average in which we very specifically just add up the numbers directly and divide by the total number. But in this case, it's another kind of average in which I first take the square. Right, from there to there, I first take the square, and then I take the mean, and then I take the root again. So this is like, if you like, a different kind of average, and this kind of average has a name. It's called the root mean square. Root mean square. Now the short form is just the RMS. So this is the R. Let's say the RMS voltage. And as a symbol, it might be written as V with the subscript RMS. So VRMS is equal to the peak voltage V0 divided by root 2. Okay, and I'll just very quickly finish off by mentioning that we also know that the current follows the same formula. That means that the current is equal to the peak current I0 times sine omega t. So in other words, we can carry through the same idea for currents and get an RMS current. So I can have also, instead of voltage, I can have RMS current, and instead of VRMS, I can imagine an IRMS, which would be equal to, instead of V0 over root 2, I can also have I0 over root 2 for the current.